So my name's Luke. This is me here. So I'm a master's student at UCS. I'm kind of on the other side where I'm just starting my thesis. So I'm looking at brain-computer interface and virtual reality technology in the field of skill acquisition and learning, which we'll get into in detail. So this talk is going to be about my thesis and my proposed research. I also work at a startup called uCat, which is we have a nice little robotic cat, which is our mascot, and we work with paralyzed patients to try to restore speech and movement using brain-computer interface. So we work with labs that are decoding speech from the brain, so someone types a certain word and then we detect what that word is, and we add a VR layer on top of it. So there's a few moving parts, it's a little bit complicated, but I'll get to that at the end. So I wanted to think about this concept of intelligence augmentation, right? So this is something we talk about in transhumanism, is this idea of upgrading our intelligence. And so very broadly, I see it in three kind of phases. So where we're at right now, or where we have been for some time, is just a one-way communication from the internet, or even previously through books and libraries and that kind of thing. So we consume information, we write it down, hopefully we remember it, and that's kind of how we learn, or we learn from a teacher and they're dictating to us, right? What we're kind of entering now is this stage of neurofeedback and using brain technologies to reinforce this process. So basically, we're using technology to detect what's going on in our brain as we learn, and then reinforcing that so that we can learn more effectively, which will inevitably lead to things like AI being implanted in the brain. So this is like the most hazy and kind of unknown part of this path at the moment, but you'll see how this research could tie into that kind of outcome. So yeah, today we'll be focusing on this middle phase, and this is what my research is looking at. So you need to understand a little bit about the brain in order to understand this talk. So our brains have this incredible ability to change, right? So every time we have an experience in life, there's a physical change happening in the brain, known as neural plasticity. And so this is a concept where neurons in our brain are firing and talking to each other, and the strength between those two neurons is becoming stronger and stronger over time. So every time we repeat a skill or perform an action, we become more familiar with that skill, and it becomes easier and easier to strengthen that connection over time. So what we're doing with neurofeedback is using EEG, which is basically a set of electrodes that one can put on their head, or a small electrode arrays that detect electrical signals, which happens anytime the brain fires and does anything. As they're performing a task, they're going to wear one of these headsets, and then some of their metrics and performance statistics are going to be displayed to them on a screen, or orally, or haptically. Somehow they're going to get some sort of feedback on how they're doing with this task. And then that is going to, obviously they're going to read that, or they're going to listen to that, and their brain is going to understand, oh, okay, I need to course correct right now. I need to change my performance in this way or that way. And so this way we can kind of recursively make a loop of feedback in order to have the most optimal learning possible. So if you think about a traditional learning model, we have one teacher and maybe 30 students, right? And there's a lot of difficulties with that, because maybe one student is a little bit further ahead than another one. Maybe another student doesn't quite grasp this particular concept. There's many issues that can arise. And a teacher doesn't have the time or the resources to create 30 different curriculums, right? And so what happens is a lot of students end up left behind. So one possible future is we use BCIs and VR to have individualized learning curriculums that is perfect for your brain, right? So we could have each task broken down into 30 different subtasks, or slightly different tasks, that will allow all students to proceed in their learning and to benefit, right? So caters to different skill levels. Another benefit is that unconsciously we may be committing errors in the task we're performing, but we might not know. But this could be detectable at the level of the EEG that's on your head. So this could provide even more benefit than, say, a real-life coach or teacher who may not pick up on that. And then eventually, hopefully, we can make predictive models of how difficult content needs to be for each student. So let's say you're using one of these systems, and it'll say, okay, based on your performance, in 2 weeks, you need to look at this content. This will be perfect for you. In 1 month, you need to look at this content. This will be perfect. Or maybe this is too difficult and we need to take it back. So VR is already fantastic for this. There's a lot of research that points to various aspects of VR being fantastic for learning. So these complex environments that we can be in are really, really conducive to learning, as we've found. So in VR now, there's a lot of programs, particularly in the medical sphere, for medical training, where people have a virtual avatar of a cadaver or a heart or a brain in order to learn more effectively how to interact with that organ and learn about that organ. And this has been very effective. It's also highly interactive, so instead of just writing something down and listening to something, you're actually grabbing it, you're using your controllers, you're hearing things, and it's completely immersive. And haptic feedback with vibration and that sort of thing plays into that as well. So on top of this, what I want to do is use brain-computer interface to monitor the state of a user while they're in a VR experience. So they're in a VR learning experience, they're learning a skill, they're being educated, and simultaneously we can detect how engaged they are. So is it too easy? Is it too hard? Is it fun? Do you enjoy that kind of activity? And also the cognitive workload, which is basically just determining how much strain is being put on your brain right now. Like, yeah, if this task is super easy, then it's going to be a low cognitive workload. If it's too difficult, it will be a high cognitive workload. So it's about finding that perfect balance. So to give an example, let's say we're teaching someone how to fire a bow and arrow in VR. And so there are lots of archery VR programs that I've used, and they're really fun. But what we want to do, if we're trying to teach them this skill optimally, is keep them in this flow state using these neuropsychological markers that I just mentioned. So let's say we start out super close to the target, we're hitting bullseyes 90% of the time, feeling good, but then eventually you're like, this is kind of boring, like I'm not really progressing, right? So the engagement is low. Additionally, the cognitive workload is low. You're not really having to spend many mental resources on this task, so you're more likely to be distracted, pull out your phone, whatever it is. So eventually we can detect this, and it's like, boom, this is a perfect distance, right? So we have a high level of engagement, we're having a lot of fun, we're optimally getting better at this task, and our cognitive workload is such that it's enough to drive us, but it's not so much that it's too much. Some time passes, and then eventually maybe this person fatigues, right? So now they're not engaged anymore because they're just too tired, right? So time is another factor that we have to take into account when we're creating these optimal schedules. And the cognitive workload is going to be too high, they're going to start to get exhausted, it's not going to be good. So at this point, we're either going to move the target back to be closer, or just take a break, right? So spacing these tasks out and having optimal breaks is another really important aspect of this, and I'll come back to that in a second. So some applications of my research that could come out of it. This is the only picture I could find for this, I thought it was quite funny. So basically, I would love, my dream is to have a generalizable model of learning that we can apply to any task. So you could have an API where a teacher is going to plug in their particular curriculum, or someone's going to plug in their particular task, and hopefully it doesn't matter what the task is, it just matters how engaged are you and how much cognitive workload is going on. So this could have massive effects if in the future when DCIs and VR are much cheaper and works better, it's faster, we have better machine learning algorithms, everything trickles down. I think this could be of a lot of benefit. Also, existing psychological theories and neuroscience theories could be gamified and applied to this sort of BCI VR system. So one such model is the spaced repetition effect, which basically says that cramming for an exam is not actually as effective as having short bursts and then having breaks. Because in the breaks is when your brain actually puts together that information, especially during sleep. So, this paper that I found was basically explaining that like at a neuroscience level, at a cellular level, we found that, it's much more effective for long-term potentiation, which is basically the strengthening of neurons, so as I described at the start, over time. It's much more effective when you space it out. So we can plug this into the algorithm as well. Another kind of theory that we can look at is this zone of proximal development, where this point that you're at now is your current skill level, this yellow dot, and this outer ring is a task that is just going to be impossible for you. So your range of ability is kind of in between there somewhere. And so in this model, we have a teacher or some invasive brain implants, and the the decoding algorithms for speech, which is essentially to say they think something and the text comes up on the screen of what they were thinking, is becoming extremely effective. So it's at about 65 words per minute now, which is faster than most people can type on a phone. So some of these paralyzed people are going to be able to communicate faster and better than able-bodied people quite soon, even now. And so we're hooking these up to virtual avatars as well. So to regain that autonomy that people have lost through paralysis, we give them a face, and we give them emotion, we give them expression. And so this is some of the work that I'm doing. This is our little robot cat, this is uCat. And so this is our dream. This is a prototype we're building right now. It's a VR experience for paralyzed patients who have an invasive brain-computer interface, which is a mouthful. But essentially we're trying to restore speech, restore motor function, and end paralysis in the metaverse. So it's a lofty goal, but we're really excited. That's awesome. So that's it. Thanks.
Great presentation, by the way. Is there anything around PTSD where there's really established long-term potentiation that you think this sort of system could be adapted to have a remedial effect or in some way?
Yeah, for sure. So I've seen examples of that in a VR setting without the BCI so far, but there have been VR simulations where soldiers who have PTSD will go back into a simulation of a war environment, which can be triggering for sure, but they're accompanied by a therapist, and it's all consensual, and it's very gradual, and that's been very effective. So the immersion that I described for learning, it's all the same, right? Instead of learning a skill, you're learning to not be so afraid of life. Like you're learning to get over your trauma, right? It's
in terms of what is actually benefit, what is actually learning.
Yeah.
So then, I guess what's happening around that, like from a machine learning perspective?
So yeah, good question. In my case, the models are being trained around whatever markers we're looking at. So I looked at engagement and cognitive behavior, right? So there are already a lot of data sets out there publicly to pre-train a model to detect that. So that said, you do need to train it for the individual user. So it takes quite a lot of trials and a lot of training to get the data to a point where you can reliably detect if someone's engaged.
Would you be asking the users questions? What I mean is like, okay, so you want to look at how fast someone's learning. So then you need to be able to test to figure that out, right? Based on you've got the EEG output, but so what, right? You need to then measure that against something quantifiable.
So the quantifiability comes from the game design, but the EEG accuracy is only really useful in the initial phase of are you engaged or are you paying attention or how much cognitive.
So you're just using it for attention.
Correct. Yeah, all of those kinds of states, right? Or it doesn't really matter what the state is. It's just some psychological or neurological state. But then you're right. The game. So this is the idea: is the VR experience should change in response to that, right? And then yes, there'll need to be a metric to say, did you learn correctly, right? Whether that's like, did you hit the target enough times or whatever it is, and that can feed back into that. That kind of makes sense.
Does it need to change differently depending on the approach to the task? Like say, I want to pull the archery bow back this way, but then for some reason I decide to reverse my hand grip on the remote. Of course I'm going to be facing a different workload.
Right.
Like try and pull it back.
Yeah, for sure.
So is that handled already in the training?
So yeah, that would be something again in the VR game design that should be accounted for. So depending on the variables of the rotation of your arm, right, you can say like, okay, that's wrong, and then the user can be course corrected in that sort of way. I guess the use case here is if the technique is more or less correct, but they just need to practice the actual skill, if that makes sense. So they're in a perfect technique per se, but they're doing it within the bounds of the game already, and then we're just getting into that next level. Yeah.
Limitations. Anything that jumped out to you that you'd like to highlight?
Yeah. So can be ergonomically annoying to wear a VR headset can be. There are headsets now that are combining the two into one device, so that's kind of tackling that problem. People are afraid of PCIs. That's another thing. They, think of Neuralink and that sort of thing, and which is the same technology. It's just invasive instead of non-invasive, and they get really afraid, which is understandable. And there are definitely scary aspects to it, but they just don't understand it initially. So there's a barrier to entry. Like I had one of those EG headsets as well. It was the Muse, and I gave it to my girlfriend, and she freaked out. And it took 20 minutes, like for me, like it's fine, like you can put it on. And that was just like a meditation app. Those are the big ones.
What about, so cognitive workload usually is on range, and so for some, the upper limits, the amount of camera that will come for benefit of the individual, how is that taken into consideration instead of just cutting them off and not giving them that opportunity to test those limits?
So you're saying like a generic range of skill as opposed to like a personal range.
Well, that you can, measuring cognitive workload, right? And the upper limit set. So then the game changes, right? Any consideration about, well, when does the game change for the individual? And could the individual be missing out opportunity to stretch themselves just that little bit more if the game changes a little bit too quickly?
I see. Yeah, well, that's a really good question, and that's a question of calibration. I think. But I think ideally it would have, your range of cognitive workload. Like, what do you find hard, right? Like, and there would be some training, and it was a training phase initially.
Yeah.
That would determine that, right? So the range wouldn't be the same for everyone, because someone might have already done it. So maybe it's super easy for them to start, right? And they need a really, really full charge.
Tough one, because sometimes we think it's too difficult, but we
Yeah.
surprise ourselves.
That's right, and there's a lot of research pointing at this idea of just pushing past that point of
Yes.
difficulty where you find it's a little bit too hard, and then resting is optimal. So that also, like I mentioned, existing psychological theories can be applied, right? So
Yeah, in the example you talked about with the 3 patients
yes,
doing word recognition,
yeah,
or at least word creation. I think you said that was an invasive.
Correct.
Yeah. So from your research, are we getting closer to sort of non-invasive technology that can get the same level of
it's a really good question.
like fMRI mold is one that I'm thinking of.
Yeah.
Oxygen level differentiation. That sort of thing.
For speech detection, the non-invasive is still quite limited. So you see these paralyzed patients, and they're obviously quite willing to undertake a surgery and put a chip in their brain if that's what it takes, because they can't speak, they can't walk, they're in wheelchairs. But cognitively, they're completely intact. It's just the connections to their peripheral nervous system that's the issue. So yeah, the non-invasive.
She is able to use very slowly another method of communication.
That's right.
So she could that way.
Yeah, that's right. That's right. Yeah, we're pretty convinced that these people are saying what they're saying. But it's a good question. Yes.
Thanks. Hi, great presentation.
Thanks.
I love the topic. 2 questions. I'm sorry I wasn't first.
It's alright.
The first one's around the role of the observer. So that idea that if you're not there in the forest to hear or wherever to hear a tree fall, that it make a sound. It seems as though internally we would have our own biofeedback back in terms of education and reinforcing those pathways we want to reinforce in others away. By providing external feedback, do we then become dependent on a sort of a third party to a relationship rather than the healthy 2-party relationship? But do we, your thoughts on that observer effect? In fact, that's kind of a
Yeah, it's a great question. Not something I've thought about a lot, but I think my gut would say that, in the age of distraction, most people are complaining about a lack of being able to focus and get work done and learn effectively and that sort of thing, especially in schools, COVID, ChatGPT, TikTok, it's looking